give him the link. I mean, his friend as something.
Yeah, can you give me the Zoom link?
Yeah, sure.
No. Let him know the link.
Our speaker. Can you see?
Hello.
Okay.
Okay.
Yeah, I think
Okay. Yeah, I already received. Yeah, just received. Thank you.
Oh. Hello, everyone. Thank you for coming the first lecture of the series, Higgs inflation and unitarity. So from today, in this week, we will have 5 lectures by Dr. Min-Si He from IBS. So the lecture will be about 4 hours, including break time. It will start at about 2 p.m. for all days except for Thursday, which will start at 10 a.m. So let's welcome our lecture speaker.
Thank you very much for the introduction. Yeah, probably not 4 hours that long, but I tried to. Yeah. Okay. Yeah. So maybe I should first talk about my plan of this lecture. Yeah. No. First of all, I want to thank you, Professor Kaur, for inviting me, give this opportunity, and it's my first time to give some kind of lecture, so I'm a bit nervous. And yeah. Anyway, first I want to talk about the plant, the content of my lectures. So actually, I prepare 5 lectures, and with additional lecture 0, because probably not all of you are working on this cosmology or not familiar with this inflation thing, so I would probably talk about some basics of this cosmology, hot Big Bang cosmology, hot Big Bang. Cosmology. Is it big enough to see? Okay. And also basics about inflation. Or more specifically, it's just canonical single field inflation, a slow roll inflation. Yeah, because we will use this thing for the subsequent calculations, most of the subsequent calculations. Of course, maybe we will later get involved into some two-field model, but all of them can be described in a way as an effective single field inflation. So this is very important for us. Yeah. And then we go to lecture 1. So both lecture 0 and 1 will be today's content. I will introduce the so-called metric Higgs inflation. It's the original version of Higgs inflation. And we just have GR and the Higgs field and coupling between them. Okay. And within this, I will talk about, of course, the inflation dynamics and predictions and the cutoff scale, which related to our title, the unitarity. Because the cutoff scale in this model is not trivial. It's, I will let you know later. And then the preheating process in this model. And and during the preheating process, you see that in this model, you have some unitarity violation during preheating because the cutoff scale of this model is low, but the particle produced during preheating is, have much higher momentum than this cutoff scale. So you have strong coupling during this violation. So this is the today's content. Okay. And then in tomorrow lecture 2, I will talk about, because we have some unitarity violation, so actually this is a very particle physics motivated model and it has pretty good properties, so we try to save it, because if we have strong coupling, we don't know how to calculate, we only know perturbation. So we try to UV extend this model such that we can still come back to our familiar perturbative method, and which we call it the so-called the Higgs R-square model. And in this case, you see that we extend the Higgs inflation with an R-square term, which can be, can originate in the one-loop quantum correction. I will show later. And firstly, I will introduce a method which involves the so-called conformal mode. I'll just leave the explanation tomorrow. And with this conformal mode, we can have a frame-independent way to calculate the unitarity violation scale or the cutoff scale. As I'll show you later, this cutoff scale calculation is not so trivial without this kind of method, okay? For cutoff scale calculation. Okay, and yeah, because I just try to control the length of each lecture, so I just move this to here, not to talk about it today. And then I will introduce the inflation dynamics and reheating briefly in this model, because this is not our main topic about reheating. So, yeah, if we talk about reheating, there could be another lecture. And R square as one loop correction. Quantum correction. In the large and large C limit. C is the nominal coupling between Higgs and the Ricci scale, which already appears in this original model. And then on Wednesday, I will try to talk about another way to avoid this unitarity violation, is to change the gravity formulation to the so-called Palatini formalism. And the Higgs inflation in this Palatini formalism, indeed, it does not have this unitarity violation, although the cutoff scale is still much lower than the Planck scale. So first I will introduce what is Palatini formalism, and then calculate the cutoff scale. And then I show you that during preheating, there's no unitarity violation in this model. Okay. And still, as I said, the cutoff scale is still low. So one may wonder, yeah, probably we can add some R square to see what happens, whether we can UV extend the cutoff scale to Planck or something. So I will talk about this in the last of this lecture 3. And the answer actually is no, we cannot UV extend by this R square. And so I will try to talk about some other attempts for this UV extension. Yeah, but anyway, so far this is still an open question, how to UV extend this. Okay, so nobody knows the answer yet. So in lecture 4, I'll talk about another gravity formalism, the Einstein-Cartan formalism. And what's interesting in this, of course, I have to first introduce this. What is this? And then I will show you that this Einstein-Cartan Higgs inflation can serve as a general framework for a large class of inflation models, including this metric and this Palatini case. So it can smoothly connect these two cases. And then I talk about some inflation things and cutoff scale. Okay. And these two seemingly very different model actually is, can be connected smoothly in this framework. And then in this framework, we can show you, how the cutoff scale changed from this one to that one, and how unitarity violation disappear here and appear there. Yeah, and some of the result is still preliminary because I'm still working on that. And the UV extension of this general framework. As you can expect it, because I said we still don't know how to UV extend this. So actually, this part can only UV extend, how to say, the parameter space close to the metric case. Not when we try to approach this limit, this UV extension will fail. Yeah. But since I try to make this lecture for shorter, so I move this preheating discussion in this to here. The Einstein-Cartan Higgs inflation. And this is based on some preliminary result. Preliminary result. Okay. And then I again use this one loop correction. Try to show you this can work to some extent. And also discuss whether this one loop can really UV extend. And its limitation. So this is the content for all 5 lectures. Okay. So I will start from lecture 0. And actually, I prepare many things for this lecture 0, but probably I don't need to show all of them because you must have already known some of them. And in this lecture, I use the coordinates like, no, the units like Planck, h bar, c, and Boltzmann constant equal 1, and Planck, reduced Planck mass is square root a pi g. G is the Newton constant, and this is 10 to 18 GeV. Okay. And minus plus plus, maybe different convention from particle physics. Yeah. Okay. So as you know, some history thing. The Hubble's law in 1929, when he observed the sapphires, and he found that the galaxies is moving away from us, something like this, and there are many dots. Okay. This is the redshift velocity. This is the distance. And yeah, moving away from us. And also, these galaxies, the farther away from us, it moves faster, have a higher redshift velocity. So Hubble think, oh, probably this is not because of the, galaxy movement itself, the peculiar motion, but because of the universe is now expanding. So if we write this v, velocity v, is a derivative of some ax. X is the so-called co-moving distance. Means that if the universe do not expand, then, how to say? A is the so-called scale factor that describe the expansion of the universe. Okay, X is the co-moving distance. It means that if we use only X, then we are expanding or contracting with the universe. So we do not feel anything. So this X describes the peculiar motion of the galaxies itself. For example, the Earth going around the sun, something like that. But A is when, even if we are sitting still, we do not move, then somehow the galaxies, the distance between the galaxies and us is growing. So we can write a dot is the time derivative, okay? A something like this. If the galaxies, we assume it is not moving, then this will become something like a dot x. And if we divide it by a times a, it means that we define the so-called Hubble constant or Hubble parameter. So this is the so-called Hubble's law. This is Hubble parameter. Of course, this thing measured by Hubble is he can measure the Hubble parameter today, which we denote as h naught. But actually, the Hubble can be time dependent. I mean, at different times of the evolution of the universe, this Hubble can be time dependent. So it can be different. Okay. And the physical meaning of this Hubble parameter is that, of course, here is the expansion rate. Expansion rate. So, which means that if it has a dimension, mass dimension 1, so it means that if we take the inverse, it means that the time scale that the universe becomes twice as large as itself. The universe becomes twice as large. Twice as large. And if we multiply by c, which is 1, then it also gives you the scale, the scale of the universe, length scale of the universe, observable universe. Okay. And usually we use, when we discuss inflation, we use some another useful parameter as time, and another quantity as time, which is the E-fold number. If you write Hubble, this is defined as A dot over A, then you can easily write it like log A to the time derivative of log A. And then you can write this in terms of some ratio with the initial A. Initial A is just you set as initial value of A, because A here in a flat universe, A has no physical meaning. So you can always rescale it. So you can just choose some initial condition. And we define this log A over A initial as the E-fold number, which means that the universe expands e to the n times as the initial size. Okay, so we will use this NE. Okay, so remember this relation, D NE is H to T. So Hubble time E4. Okay. Of course, rigorously this should be something like this. So since we observe the universe is expanding, so if we go back in time, then we will expect some very hot and dense initial condition for our universe, which means that, so this is the so-called the hot Big Bang theory. Okay. And this so-called the initial condition, they usually call it the singularity, because they expect that if we go to some, maybe infinitely small size, then it's like a point. And after the Big Bang, the classical evolution of the universe begins, and we can describe by GR and the quantum fields on this. Okay. And hot, Big Bang, hot means there are a lot of matters, like standard model particles, and they are moving in relativistic velocities or something like that. Okay. And on large scale, we can treat this matter field in this universe as a perfect fluid. Perfect fluid, which means that this T mu nu, we just have this some rho p something. I forgot upper or lower, but anyway, something like this. And perfect fluid means that this P can be parameterized as this W rho for different kind of matter. This W take different values. For example, for relativistic particles, we usually call it radiation. W is 1/3. For dust or matter, when we say matter, we usually say the pressureless dust. Then this should be 0. For cosmological constant, this is -1, something like that. And for the spatial curvature, maybe I shouldn't say this, but yeah, anyway. For spatial curvature, maybe this is K, maybe K. 2, it's maybe this 3. So 2, 3, -3 or 1/2, something like that. Yeah. Yeah. Of course, then the total energy density of the universe then will be the sum of all these kind of radiation, matter, cosmological constant, curvature, something like that. But this hot Big Bang is not enough. Okay. Because it has some it suffers from some initial condition problems. Yeah, it's so-called the horizon problem. And flatness problem. Something like that. And I'm not sure whether I should explain this very detailed. Maybe no, but basically, this horizon problem, it says that if we start from some initial singularity or something, and then the universe expands, then actually more and more things outside this, I mean, initially they are causally disconnected because the light have no time to travel, and they have not enough time to communicate with each other. Then when they, at late time, when they enter the Hubble horizon, we can see these two previously causally disconnected things. But then what we see on the CMB is that they look almost the same. Not only they look almost the same, everything that previously causally disconnected looks almost the same. This is, I mean, a very huge coincidence if there's no things that make them look like the same. So this is the so-called horizon problem. And the so-called flatness problem is that we observe the universe as a very flat, I mean, the spatial curvature is very flat. So it means that if we describe our universe with the Friedman, Robertson, Walker metric, this K is the spatial curvature. K equals 0 is flat. Plus minus 1 is open and closed universe. And what we can observe today is that K is very, very close to 1. It's this is okay. This is not a problem. But the problem is that if we, use this Higgs Big Bang theory, we will find that actually the omega k is defined as omega k. The k over something, k over minus k over h a squared h squared. This is the scale factor, Hubble parameter. This omega k basically means that the curvature, the fraction of the energy density, how much curvature is in the total energy density of the universe. If this equal 1 means that this curvature dominates the whole universe, okay? Not the radiation, not the matter, but the curvature, spatial curvature itself. And what we observe today is that this is very close to 0. But according to the Higgs Big Bang theory, you can calculate it. And this absolute value actually is growing with time. So this is very strange. If this is growing with time, and now it is almost 0, it means that at the earlier stage, this is even much, much smaller. So this is an initial problem. For example, at BBN, Big Bang nucleosynthesis, earlier time, this should be smaller than 10 to minus 16, something like that. So we have to fine-tune this thing and to be flat, and fine-tune everything outside the horizon to be the same. And then today we see it, they are the same.
I have one simple question. So about the horizon problem, you said that the two quadratic disconnected can be look similar at this and B observation, but exactly the quantity that looks same. How can you define the similarity?
Temperature.
Only temperature, right?
Yeah. Yeah.
Color.
Yeah. Yes. And yeah, also, yes. And also, how to say, the large scale structure, the galaxy distribution, something like that. Yeah, they are all homogeneous, isotropic, something like that. Yeah. So I think, yeah. So you want to know some like vector component or something?
No, so I'm just curious what kind of the factor that you
Yeah.
the similarity.
Yeah, the temperature, actually. Yeah, temperature. For example, if the universe is not so homogeneous, then probably here you have more matter and this less, then the gravitational potential, this will be like large gravitational potential, this smaller. So the temperature will tend to be colder here than here. So you will have large, for example, dipole or something. But actually, no, you just found it's so homogeneous with only small fluctuations, which is the amplitude is 10 to minus 5, something like that. Yes. So that's why people consider this inflation scenario. to explain the initial condition for the Hop Big Bang theory. Okay, so session 2. Okay. Okay. So in 1981, Alan Guth, he proposed, okay, inflation can solve these problems. So what is inflation? Inflation, I think it's an accelerated, expanding of the universe. They call it inflation. What is accelerated? So as I told you before, scale factor A, maybe I should, we will use k equals 0 from now on, okay, because we observe the universe is flat now, okay, that is the FLW metric. We use A to describe the expansion of the universe. A dot is the expansion rate, okay? So A dot dot will be the acceleration. So if it is accelerated, this should be positive. Then, if it's decelerated, it's negative, okay? Yeah, so inflation here means it is positive in the early universe. We need such a period, or not we need, but such a period can be one way to solve these problems. Okay. So where can we find this? So we have Hubble for A dot over A. Then this means that H dot dot is something like this, okay? So it means that H dot dot plus H square should be larger than 0, because this is A dot dot over A.
H dot.
Sorry. Yes. Yeah, you're right. Yeah. H dot, sorry. H dot plus H square. And which also means that time derivative of 1 over AH is smaller than 0. You can easily derive this. Then immediately you will see that we can solve the flatness problem, right? Omega k is like this. So if we have such kind of period, and if it is long enough, then this will decrease. Even if it is, for example, order 1 or something, it will decrease. If it is long enough, then it will decrease into a very, very small number. And then you can evolve it. Until today, it can still be quite small. So this is immediate result. I mean, the answer to solve this flatness problem. You can also solve the horizon problem. yeah, it's a bit difficult to explain. I can draw some figure, but yeah, I can draw some figure maybe. This is a conformal diagram. We use the conformal coordinate. This is some kind of time. We call it co-moving conformal time. Conformal time. This is, and we are here now, today. And if we draw the past line cone, okay, so what we can see at most is these 2 points. This is x is the co-moving coordinate. Okay. Then, if this is the Big Bang time, Big Bang. If this is the Big Bang, then after the Big Bang, at some point, we have CMB. CMB. Which means that this CMB at this point, at most, they know the information around this scale. Which means that these 2 points, they cannot connect to each other at this moment or in the past. They cannot. But today, we see these 2 points. They look the same. This is the horizon problem. But now, use inflation, we extend the time to even, farther in the past. It gives them the chance to causally connect it with each other. Okay, this is how inflation solve it. In terms of equation, you can calculate the so-called co-moving horizon, which characterized by this conformal time. Conformal time is defined as dt over a. A is scale factor. Okay, so this means that the light, how to say, not the light, but yeah, at most the distance that you can causally connect it to each other in the past. Maybe now you cannot, but in the past you can, and this is characterized by this quantity. And you can rewrite this integration in terms of AH. As I mentioned here, AH is decreasing with time, which means that this quantity is larger in the past. So the particle horizon received large contribution in the past, and it can be very large in the past, which means that particle horizon means that you can, in the past, at some moment, you can causally connect it with each other. And then as the universe expands, probably now, for example, at this moment, you are causally disconnected. But since they already communicated with each other, so it is not surprising that they can be almost the same, because probably at this time they get equilibrium or something. So yeah, and they can be similar to each other. And this is the, roughly speaking, this is the solution of the horizon problem. Then the question now is that how to realize inflation. to realize inflation. So yeah, we should have a look at the Einstein equation. If you input this Friedman, Robertson, Walker metric, then you will find the so-called Hubble equation. This rho is energy density of everything in the universe. Okay. This is Planck, reduced Planck mass. Of course, now we can neglect this K, but this is, I mean, for general K. Okay. But you can neglect, we will neglect it for simplicity. And also this is Einstein equation. And this is the conservation of the T mu nu. Give you some kind of continuity equation. So rho dot is some 3h times rho plus p. And if we assume some specific component dominate the universe, then we use this W to parameterize P. Then this can be written in terms of rho only. 1 plus simple. Then from these two equations, you can derive H dot, which is important to characterize. And then you plus this because it's H dot plus H squared. H dot plus H squared. Then you realize that if this is minus sign, okay? If we want this to be positive, then W should be smaller than minus 1/3. Okay. This is the requirement for the meta sector to realize inflation. Okay, so as you can see, the pressure is minus something rho. Oh, sorry, rho. So it's providing some negative pressure. Means that it is pushing things away. Of course, we already have one candidate, lambda, cosmological constant, which W equals -1. Yeah, this can give you inflation, but it will never end. So it's just expand forever. then we will not exist. So we need something not that extreme, a little bit mild, so that inflation can stop and then structure formation can start and we can exist in this universe. So we try to make use of some scalar field, which is probably the second simplest candidate. Okay, now we write down some Lagrangian. Einstein-Hilbert term from GR, canonical kinetic term for scalar field, potential for scalar field. Okay. And yeah. And since we want to have a kind of homogeneous isotropic universe, so at the leading order, or as a background, as a classical background, we assume this to be only t dependent. Okay, and also we will use flat Friedman, which means that k equals 0. Then you can derive the equation motion for phi dot dot, because there's no spatial dependence, so there's no gradient. Okay. Yeah, phi dot dot plus 3h phi dot minus some potential, some mass or interaction. So here, Hubble or the cosmic expansion is like a friction term of some oscillator, harmonic oscillator. If this is a mass term and if we omit this, then this is harmonic oscillator. But now you have some damping by this Hubble friction, we call it. And also as I showed you before, the Hubble equation, no, Friedman equation. Friedman equation is simply rho. Rho, energy density of the scalar field is kinetic term plus potential. So these two simple equations. And we define this W equation of state parameter. P divided by rho the kinetic term minus potential divided by kinetic term plus potential. This can be derived from the T mu nu and the spatial component, time component. Okay. Then from this you can guess if the kinetic term is negligible compared with V. If kinetic term is much smaller than V, then this is minus V. But it's not exactly 0. So somehow deviate from this. Maybe a little bit larger than this. So which means that if we have such kind of canonical scalar field with some potential, then to realize inflation, we just need, during inflation, the potential term dominates the energy density. Then you will have so-called inflation. And if we wanted to stop, then you just need to make the kinetic term larger. Then it will finally, W will become larger than minus 1/3, then inflation stops. Then the rest to do is to produce standard model particles, as we can see today. Okay. And this kind of kinetic term, much smaller than the potential term, which means that the scalar field actually is slowly moving. So we call this the slow roll inflation. It's like the field is slowly rolling down the potential. Of course, there's some kind of K inflation, which proposed by Professor Mukhanov. And yeah, but I will not talk about that. In that case, the kinetic term is the dominant one. Okay. Okay, so this is one condition for slow roll inflation. Okay, you need small kinetic term. The second, okay, this is first. The second is that, as I said, it should last long enough to solve the horizon problem and the flatness problem. It should last long enough. Okay, this is important. Then for each condition, we define a quantity, this so-called slow roll parameters. The first one is we call it epsilon 1, the first slow roll parameter, which is defined as minus h dot over h squared. Okay, and the second one we define as epsilon 1 minus epsilon 1 dot over 2h epsilon 1. Usually in the literature they use eta for this, but since I have already used for conformal time, so I just use epsilon 2. Okay. Then the meaning, for example, the meaning of this epsilon 1 is very simple. If you start from this Friedmann equation, you can derive h dot. Yeah, you just take a time derivative. Then you define. You can find this h dot is proportional to the. I forgot the coefficient. Proportional to the kinetic term. Only. There's no potential term. Okay, so h dot, but kinetic term in the numerator. Okay, it's kind of kinetic term in the numerator. H squared here is the kinetic term plus v. This we require them to be slow motion. Required it to be much smaller than 1. Much smaller than 1. So it is equivalent to say much smaller than v. Okay? So the meaning of slow roll parameter is kinetic term is subdominant, potential dominant. The second one, if you put this thing again, you will find, if you require this to be smaller than 1, then you will find that this, okay, so I write it down, okay, minus dot dot h phi dot. Dot dot is the first term, h phi dot, second term. This much smaller than 1 means the friction term dominate over the acceleration term. Yeah. So these two conditions called the slow roll condition. So slow roll is the kinetic energy smaller than potential. Long enough time means it accelerating in a very slow rate. So the kinetic energy needs a very long time to catch up with the potential energy. So it can last for long enough time. You have to satisfy both to have slow inflation, okay? So the end of slow inflation is the violation of one of them. For example, epsilon equal 1 or epsilon 2 equal 1, something like that. Or, okay? Then if the slow condition are satisfied, then we have the so-called the slow roll approximation. Which give you the two approximate equation. The one is that we neglect the acceleration term because the friction term dominates. The Friedman equation, we neglect the kinetic term, only the potential dominates. And this is almost constant during inflation because phi dot is small, so it changes very slowly. Okay. Then from this, we can express epsilon 1 and epsilon 2 in terms of the potential. This can be kind of homework if you haven't done this before. Yeah, it's very easy to derive. Okay. So epsilon 2 is minus epsilon 1 plus something. So now, this is only approximation, okay? Under the slow approximation, you can approximate that definition with only potential. So the potential information is enough to know whether we have slow inflation, okay? This is very useful because once we know the potential and a canonical kinetic term, then you can easily derive this too. And we define this as epsilon V1. V means the potential, okay? And we define this part, only this part, as V2, epsilon V2. So epsilon 2 is minus epsilon 1 plus epsilon V1 because this is epsilon 1, V1 minus V1 plus V2, yeah. And we require this to be much smaller than 1, then we have the slow roll inflation. Yeah, so this is important. You should remember. And very useful, very useful. Yeah, then I will briefly mention like inflation scale. When we talk about inflation scale, okay, we are talking about like, because from the Friedman equation, 3 m plus square h square equal v. Actually, it's rho, right? Rho. So the inflation scale, lambda inflation, is roughly speaking 3 Planck square 1/4. The dimension is 1, this is 4, so it's 1/4, which is, yeah, of course, during inflation. During inflation. It's potential during inflation. And during inflation, the Hubble scale during inflation, from this, you can easily easily. Of course, this is smaller than inflation scale. Okay. So actually, usually people care about this because this Hubble scale during inflation means the scale below which, if you have, for example, if you have a particle, then the mass scale is smaller than h inflation, then actually it can be excited. I mean, when we talk about heavy particle, light particle, we compare with this h inflation. Okay. So if the mass scale is larger, then it's heavy. If the mass scale is smaller, then it's light. This, yeah, something I want to mention. Okay. And then we go back to, maybe I already erased, but the E4 number, which is important to describe the duration of inflation. For example, the universe expands like 10 E4 means that the duration, the duration of inflation lasts for when the inflation becomes 10 e to the 10 times of the initial size. And you can change the variable.
If I just divide h in by 2 pi, I get the digital temperature. And I can compare digital temperature and the mass of the particle.
Yeah.
That may be for physical condition.
Yeah. I mean, this is just order estimation argument. Yeah. It's not rigorous. Maybe there's some pi or 2 pi coefficient. Yeah, I should separate like this. Just order estimation. Yeah. We can change the time variable. Then we can estimate, for example, given the initial field value and final field value, we can calculate the, this is approximation, use this to calculate the E4 number, duration of the inflation. Okay. So these are, important things we will use later, okay, for the Higgs inflation or some, Okay, after inflation, usually, not all the models like this, but usually, after inflation, this phi should should start oscillating, or at least the kinetic energy should start to be comparable with the potential, because we have to stop inflation and start other kind of evolution of the universe. Which means that usually this phi start to oscillate. If it can oscillate, it means that, yeah, we come back to this. If it oscillates, it means that it is quite heavy, because if it is not heavy enough, then the friction term will, just over damped. If you have an oscillator, you just over damped, and then you just go to here and stop. But we want it to start to oscillate, so this mass term must overcome this friction term. So we require some heavy mass for the inflaton after inflation. And in this case, we neglect the friction term because it is small compared with the mass. The mass is on the potential, of course. Then we have this kind of equation from there. We neglect the 3h phi dot. From this, you can rewrite is phi dot bracket dot minus phi dot square plus phi v phi. We write it in this way. Then you take an average. And this term will be averaged out because you're oscillating, switching sign or something. And you find something like this by taking average of over several periods, something like that. And then you can have an average W, which is given by this. Okay. Then we can study this thing. For example, if V is proportional to phi to the power of n, this will give you, roughly speaking, m minus 2 divided by m plus 2. Which means that this is 0 for n equal 2. This is 1 over 3 for n equal 4, for example. So from this, we can see that if you have a quadratic potential and oscillating, it means that on average, it becomes like dust, pressureless dust. Because I erased it, but W equals 0 because P is W rho. So if W equals 0, it means that it's pressureless. Okay, so if you have a quadratic potential, then you have pressureless I mean, on average, it looks like a condensate of pressureless dust, this oscillation. If you have a quartic potential, for example, 5,4, then this oscillation behaves like radiation. Just on average, it behaves like that. Okay. The coherent oscillation. Yeah. Yeah, so this is quite important. Of course, if you have a very strange potential, you can have W go to -1 if you want. It means that even if you are oscillating, you can have inflation. Yeah.
So in that equation, so W about 1/3 becomes only when n equals 4.
Yeah.
If we have some higher powers of that, then it does no longer behave as a radiation.
Yeah.
So being like a radiation is not guaranteed by just having zero mass at the point. Is this important?
It's not guaranteed by
So
having zero. No. Only this. Yeah. And I mean, even you can even have inflation in some case. Okay. I will remove this. Yeah, but pay attention. This is not talking about some particle. This is the background field. It's coherent oscillating. So it's kind of condensate. But the average value of W somehow looks like radiation or matter. Yeah. And different behaviors give different evolution of H. So the universe expands in a different way. And okay, so now we know something about this very simple, naive scalar, canonical scalar field, slow roll inflation. But I mean, how about what? I mean, it's quite naive, right? I mean, if we have some very complicated, I mean, a little bit more complicated Lagrangian like this, then this immediately useless. So
For -1 here, I can achieve that taking n equals 0,
right.
meaning the potential doesn't go at all.
Yeah. Yeah.
So at the bottom of potential,
Yeah, it behaves like a cosmological constant. Yeah. Yeah, if
constant.
yeah, constant. Yeah. No motion, just constant. Yeah. Then if I have a little bit more complicated, Lagrangian, then all these conclusion becomes useless. But fortunately, like in 1989, the Keiichi Maeda, he tells us that with maybe, yeah, of course, his paper is about more complicated Lagrangian, but anyway, we just focus on this because this is useful for our discussion about Higgs inflation. It tells us that with this conformal transformation, means, yeah, maybe I will talk about it later. Conformal transformation, then we can always remove, for example, this. We can always remove it by redefining, for example, G. Yeah. Oh, okay. Yeah. Okay. Okay. Yeah, yeah, then let's have a break. Yeah. Okay. So shall we start? Okay. So yeah, I realize that I am a bit behind, so I have to speed up. And yeah, so just now we talked about this. I mean, very simple single field canonical kinetic term, slow roll inflation, and we derive many things, and yeah, but all these things are only valid for this model. Then what if we have like more complicated, for example, non-canonical kinetic term or with some non-minimal coupling? Non-minimal coupling means that this scalar field, for example, scalar field directly coupled with the rigid scalar, this kind of coupling, we call it non-minimal coupling. Non-minimal coupling, then correspondingly, minimal coupling means this coupling constant Gaussian equals 0, okay? So here we just generally write it in this form. And what if, I mean, we have such kind of thing? Of course, without the non-minimum coupling, such kind of kinetic term, it's okay because it's single field. You can always define such a, to canonicalize this non-canonical kinetic term to be canonical. Then we can go back to what we did, what we discussed. But if you have such kind of non-minimum coupling, then it is difficult to see how we can go back to that. But fortunately, we can use this kind of conformal transformation, which means that because now we have gravity, we have g mu nu, then we can how to say, replace, oh, I should. Which replace the original g mu nu into a new g mu nu. We call it E like this. And then you replace all the metric, for example, with g e mu nu divided by f into here. Then you can recover the Einstein-Hilbert term. This E, we call it, why we use E? Because we usually call this the Einstein frame. Einstein frame means that this rigid scalar R does not couple to anything. It only appears in the Einstein-Hilbert term. We call this Einstein frame. The other, for example, this one, we call the Jordan frame. Okay, this is just some terminology. Okay, we call this Einstein frame. So this E is for Einstein frame. So for using this conformal transformation, we can always transform this kind of Lagrangian into Einstein frame with some more complicated kinetic term and modified potential. And then now you can canonicalize this. Then you rewrite everything in terms of chi. Then you go back to this. So these, then you can use all the things I derived previously. Yeah, this is a very nice thing. And also here, what we do is just to rescale the space-time metric with this vector. So we don't change anything. As long as this thing is not singular or something, then this is just a Fourier definition. It does not affect physics. And this is very important. So in Einstein frame or in Jordan frame, you get the same physics. But here you can use this result. So this is convenient. Of course, you can, if you are good enough, you can do it in Jordan frame. It's okay. Just the, how to say, the gravity part will be more complicated.
For here, the coordinate transformed or not? Coordinate.
No, we don't need to change from
Coordinate
coordinate.
does not change, only field.
Yeah.
In the usual conformal transformation, you also change the coordinate, right? But here you don't change.
In the usual, okay, now I understand what you mean. Probably we need to change the time coordinate because, yeah, as you can see, yeah, let me rewrite this. If this is the Jordan frame, mu, and then you, yeah, G, mu, something like this. And probably, yeah, F can be absorbed by A, the scale factor. So the X part can be unchanged, but T probably we need to change such that we can still write in this form. Yeah. Yeah. Okay. And now, with this, we are still in the classical level. So, yeah, probably I should skip much detail in this slide because I have not enough time. So about the quantum fluctuation. So in our picture, we have a classical field and a potential. We don't know what it is like previously or later, but we only know this part for inflation. So this scalar field slowly rolling down, if this is flat enough, slowly rolling down. And this is the classical motion. Okay, this is classical motion. So we have only phi of t. So the whole universe, I mean, this field, the whole universe is moving. Yeah. Because, yeah, probably you may ask, oh, if this field is massive, probably there's some coherence length or something. Like probably not as large as the universe. Yeah, of course, but because the slow condition requires the potential to be flat enough, so probably this coherence length can be very large because it's almost massless during inflation. Okay. And then upon this classical motion, we have very small, very small quantum fluctuation, delta phi t x. So it's like moving. Of course, the classical motion dominates the motion. So roughly speaking, it's always going down. But in different spatial position, location, there's some small difference, I mean, of this position of this inflaton, which means that, for example, if the inflaton goes to here is the end of the inflation, then the time that this inflaton can reach this point will have a bit different at different spatial point. Okay, so the inflation history at each point in the space It's a little bit different. And this is the caused this quantum fluctuation, caused by this quantum fluctuation. And yeah, we can calculate this quantum fluctuation with this, I mean, make use of this small difference of the reaching this phi n, the small difference of the time. This is so-called the delta n formalism, which proposed by Stravinsky very early time. But we will not talk about it here. And I actually don't know much. I'm not an expert on this. I just want to mention because this is very easy to understand. Okay. Anyway, now the phi becomes a classical part plus some quantum part. And this quantum part is responsible for example, CMB temperature fluctuation. Okay, delta T over T. And we have already pretty accurately measured this thing. And also, it should be responsible for large-scale structure formation. I mean, the galaxy formation, something like that, the large-scale structure. Because if you have some over-density, for example, the universe, and you have some over-density, under-density, over-density, then the over-density will cause some gravitational potential and will attract the matter to fall into the gravitational potential. Then gradually you form something and form galaxy or form something. Yeah. And this part, you don't form any galaxies, something like that. Or if this is large enough, you can form a black hole. We call primordial black hole. Okay. Yeah, this is the, okay. And usually we, how to deal with this and calculate, how to calculate this thing. We usually, yeah, Fourier expansion, yeah. For each k, you have a mode. Each k means, the k means the scale, the wavelength, not wavelength, wave number of the fluctuation. So if I draw a figure, then you understand what I mean. This is log A, means E4 number, or time, and another meaning of time, okay? This is the log scale, log of physical scale, okay? Then during inflation, this is the Hubble radius, okay, as I mentioned. During inflation, this is almost constant. And then later, we know that the universe is dominated by radiation or relativistic particles. And then dominated by, this is the matter domination, dominated by pressureless dust. And now probably it's dark energy. Okay. And we don't know this part. This is unknown. This is highly inflation model dependent. We call it reheating. This is very difficult, okay? But I will draw something here. But anyway, you know this is reheating. And then during inflation, inflation means the space is stretching out. So once you generate a fluctuation, for example, of wavelength k inverse, then this will becomes larger and larger as inflation goes on. So K here, this K is constant, okay? K will, no, sorry, my drawing is bad. K is like this. Yeah. Like this, yeah. For some specific K, or physical K, you need to divide by the scale factor, okay? Because it's growing, So for specific K, for example, this K, K1, it exits the Hubble horizon at this point. Then now it's outside the horizon, okay? Outside the horizon, super horizon. And then later, when the universe expansion is not so rapid, it's decelerating expanding, then this K comes back at some time, maybe during the radiation domination, maybe during the matter domination, maybe during dark energy domination. You don't know, but anyway, it enters at some point. So this is the K we talk about. It goes out, comes in. For different K, it exits the horizon and re-enter the horizon at different time. Larger K means shorter wavelength. Larger K exit the horizon later, but enter the horizon earlier. And small K means larger scale, larger length scale. Exit the horizon earlier, but enter the horizon later. Okay. Something like this. And so if we can calculate during inflation how these K modes behave, then we trace the superhorizon evolution, blah, 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 and then at enter moment, then we know how this quantum fluctuation during inflation affect the late universe. And fortunately, during the super horizon, I mean, when the K mode is outside horizon, such kind of perturbation, we call it curvature perturbation. Or maybe I should use R. Curvature perturbation is frozen. I mean, it's constant. So once it exits the horizon, we don't need to trace it. It's constant. We can directly know what it is when it enters the horizon. So what we need to do is just to calculate the moment it exits the horizon. Then we know what it is because it's always constant outside horizon. And I will skip how to construct some, maybe I should keep this. Construct the gauge invariant curvature perturbation or something because it's too long. But anyway, we cannot directly use delta phi, okay? We cannot use delta phi because delta phi is not gauge invariant. We know that, yeah, probably in particle physics you are more familiar with this gauge thing. So you know the physical quantities are gauge invariant, okay? So you need to construct gauge invariant quantities. But of course, this is not always true, okay? Gauge invariant does not mean physical quantity, but physical quantity is gauge invariant. So you need to construct gauge invariant and make sure it is observables. Then you can calculate things. And this RK is the or this R, I would say this R, is what is the gauge invariant and observable. We call it the curvature perturbation on comoving slides. This is the curvature perturbation in the Newtonian gauge. Probably I should skip this. Yeah, it's too long and I cannot. I forgot, but anyway, yeah. Curvature perturbation in Newtonian gauge. Newtonian. Okay, so this is gauge invariant. Of course, there are some other like uniform density slides, curvature perturbation, something. But anyway, we can use this because when we choose a gauge where that phi is 0, then it directly corresponds to this curvature perturbation. So this is important. It is gauge invariant and it is physical quantities if we can observe it. And then what we can, because this is quantum fluctuation, so you will expect that if we calculate the 1-point average, it should be 0. Okay, random variables with mean 0. So assuming this Gaussian distribution of this quantum fluctuation with the mean 0, then what is left is this the variance, right? Gaussian distribution is defined by mean value and variance. And the power spectrum is the Fourier transformed variance. So we can always, yeah. Different K, but they should coincide. And this is the so-called power spectrum.
What do you mean by this?
Ensemble average. Ensemble average. Average, ensemble average.
Average of what?
Of
Statistical ensemble average.
of curvature perturbation square.
Yeah, but usually what kind of ensemble do you assume? The previous
Okay. So actually what we calculate is something like
ensemble average,
this
vacuum expectation value.
vacuum observation value. Yeah. This is power spectrum, but this is dimension 4. And note that this K is independent of that direction because of the homogeneity isotropy. And we can define dimensionless power spectrum delta R by divided K cubed 2 pi square PRK. And we can calculate this at the horizon crossing, I mean here, when they exit the horizon. Yeah, any of them. Yeah, any of them. Then this will become yeah, I don't have time to show all the details, but so at k star h star h star. You see here, when the co-moving scale is equal to the co-moving Hubble scale, or the physical wavelength is the Hubble radius, the same. Okay, so this equal this. Then use our slow roll approximation. This is nothing but 24, this 24 pi square Planck fourth V divided by epsilon 1 at the resonance. So you see, in this single field slow roll inflation, it's very easy to calculate the power spectrum. It's just potential divided by the first slow roll parameter. And this directly relate to the observable. Like, for example, on CMB, delta T over T squared. This is 10 to minus 9 order. So you choose the CMB scale. You set it to be 10 to minus 9. Then you constrain your model, something like that. Then another observable is the running of this power spectrum. Running means how it behaves when we change the scale. For example, what's the difference of the power spectrum at this point and at this point?
What's the breakdown? Have you calculated? Is Einstein still Einstein frame?
Yeah, we in Einstein frame we do this. Yeah, I just want to argue that this can contain a large class of models. So what the calculation is still based on the simplest Lagrange. Okay, the running of this we define as the so-called scalar spectral index. Spectral index. This is defined as d power spectrum d log k. So this is also dimensionless. This is also dimensionless. Okay. And you can also calculate with this. Put this here. Then you find that this invalidated at horizon crossing. And if we put this V, we want to use V, the epsilon V, then this is minus 6 epsilon V1 plus 2 epsilon V2 at horizon crossing. And this is measured by CMB, Planck, and WMAP, something. It's very small. So the deviation of NS from 1 is very small, means that it's almost scale invariant. Okay, this is almost 0, so it's almost scale invariant. And this is measured at k star equal some scale. Okay. We can do the same thing, a similar thing, to the tensor perturbation. I mean, graviton. This is the scalar part, by the scalar field. But in GR, we have graviton. So you can do the same thing. I will not show the detail, but anyway, this power spectrum of H, okay, yeah, H is defined as a square Ij Hij, also Tt. This means transverse traceless Tt. And this scale is A times Hubble divided into 2 pi Planck square at horizon crossing. Of course, we haven't observed anything, okay? It's too small, so we only have some upper bound maybe. Then we can also define some kind of scale dependence. This again is not observed yet. It's like -2 epsilon 1. And tensor to scalar ratio. Usually we use this to talk about this inflation prediction. Tensor to scalar ratio. So by this name, this R is delta H squared divided by delta R squared. So this divided by this is 16 epsilon 1. And according to this, then you have -8 nt. And this relation, R equals -8 nt, is called the single field inflation consistency relation. So if this is violated, then probably single field is not okay.
So the definition of the spectral index. So for the tensor point, we have a logarithm in the numerator, right? While there's no logarithm in the
Maybe I miss which one? Maybe here. I forgot, sorry. I forgot.
I guess the question about what is the origin of the fluctuation, including okay, without the gravity, with gravity, what is the origin of the
Which one? This one or this one?
I think the delta H.
This one?
Yeah.
Origin. It's the gravity with gravity.
Quantum fluctuation.
Yeah, of gravity.
Okay.
Yeah. Quantum fluctuation of gravity. Yeah, of course, here we kind of assume we can quantize gravity.
When you have the take into account linear contribution.
Linear. Yes. And we have observed, we haven't observed this R yet, but this has an upper bound. It's like 0.056 at the scale of K star 0.002 megapascal. So you will always see some figure like this. This is NS, not NS -1, but NS. So you will have like 0.94, 0.96, 0.98, something, 1. And you have R. R is this, okay, R. You have 0.1, 0.05, 0, maybe 0.15, something like this. And then the observation is like this, something like this. Yeah. For the most promising models, like the Starobinsky model or Higgs inflation, the prediction is here. Why there's 2 points? Because we don't know this part. So this is highly model dependent. If the reheating is very long, then it goes like this. If it's very short, it goes like this. So then the duration, I mean the end of inflation, is at different time. So the duration of inflation is different for different reheating process. So there's ambiguity from reheating to the inflation prediction. So you have 2 points. This is for EFO number, like 50 EFO of inflation duration. This is 60 EFO, something like that. And then you have some other models like here, or here, something. These are of course ruled out, and maybe some of them is marginally okay, and also alpha attractor, something. This kind of. So when we talk about inflation, we always calculate this NS and R and see whether our model is within this observational region.
So where is the marginal?
Sorry, these are marginally okay, but within this is better.
Still, there is a reheating region in the marginal case.
Still what?
The reheating case.
Yeah. They have like 2 points, right? 2 points. We don't know the reheating, so yeah. In principle, each model should have just 1 point. Yeah, but since we don't know how the inflaton couple to the matter field, so we don't know reheating. We don't know reheating, so we have some uncertainty. So we have a line, not a point. Yeah. Then I think now we are ready to discuss the Higgs inflation.
The number of photons. So usually people take 50.
60, yeah.
How about 90, for instance?
90. It's okay. I think larger is okay, because this scale is I think the minimal to solve the horizon problem. Yeah.
But not 30.
Yeah. No.
Depending on the reheating temperature.
But yeah, probably. But according to, okay. So I don't know what kind of model we can construct, but at least, for example, if right after inflation we have some kind of meta domination, then we move this here, then probably at most, for example, you have some point. Of course, if you can somehow construct some models that have much longer, then probably yes. Yeah. Okay, so Higgs inflation. So standard model Higgs has inflaton in GR. Because, okay, we discussed all the inflation things, something. But I haven't tell you what is the inflaton. I mean, what is the scalar field? This is, I think, the biggest question about this inflation scenario because it determines everything. It determines the coupling to the matter sector, determines how the potential looks like. So it determines everything. So from the particle physics origin, so far we only have one scalar field, the standard model Higgs. Of course, I think people also study like gauge field inflation or something, but just for simplest, we use the scalar field, okay? And we know that we have a scalar field, SU2 doublet. It looks like this. Maybe you can use another parameterization, but I just like this. You have 4 scalars. Its potential is like this h square or something. So you have some symmetry breaking, spontaneous symmetry breaking, which gives you some VAV. Yeah, and this is 246 GeV. And this VAV, usually it goes to this phi 3. So this phi 3 now becomes VAV plus Higgs bosons, H. And the mass for the Higgs boson is, and this probably you know much better than me. Okay, and other 3 of them, if we take the unitary gauge, eaten by the gauge fields, of course, as normal goes on bosons. And this lambda has some interesting thing. This is the mu, the energy scale in GeV, and 10 to maybe 10 to 10 GeV around this value. 0. This is lambda. And given, yeah, then it will, according to the renormalization group running, it can run. But given different, because we haven't accurately measured the top quark mass, so in the allowed region, this lambda can run to negative for relatively large top quark mass. For smaller one, probably it's okay, it does not go to negative. Okay. Yeah, so yeah, this is one, how to say, so-called the electroweak meta stability or something. People also study this. And yeah, and also Song Chan, like he and his collaborator also make use of this running to realize the critical Higgs inflation. But I am not going to talk about this here because you can ask him, he is the expert. And I'm going to talk about here another kind of scenario. Okay, But firstly, let's see very naively whether only this setup can give you viable inflation. Okay, very naively. So we have gravity. Higgs kinetic term and Higgs potential. Of course, here I neglect the mass because it's too small compared with the inflation scale. So I will neglect the mass term. Okay, so this is the Lagrange for naive Higgs inflation. We have 4 scalars. So the kinetic term here I just for convenience, I multiply by 2. It's delta ij phi I phi j. Ij is 1, 2, 3, 4. Okay. And we can, partial. Okay. And we can use spherical coordinates, right? We can always write, given some VEF, not necessarily that one, okay? Just some VEF, vacuum expectation value. Then this is the angular part. Of course, n here is 4, but I just give it n. Then you find that in this coordinate, of course, this is like this, okay? So then we can rewrite everything in terms of phi, Einstein-Hilbert term, kinetic term for the radial direction, potential for the radial direction, angular part. Great. This is very familiar. This is just we study. But somehow we have something else here. That's okay. This part, they are massless and subdominant. So we will neglect this part, okay? We will neglect this part. Yeah. But I keep this because later when we discuss unitarity, cutoff scale, we need this. So I just keep this here. Yes, you're right. In unitarity scale, or in unitarity gauge, we can simply ignore this. Okay, we have canonical single field quartic potential. Let's see what happened. I erased something, so I need to put it here. I will use later. Power spectrum is 24 pi square m Planck force V divided by epsilon 1 at horizon crossing. Okay. Nice. Yeah. Yeah. Phi is, sorry, yeah, you're right. Phi is radial direction, spherical coordinate. Yeah.
So that partial phi means partial r phi.
No.
So what I'm confused is that typically the Cartesian coordinate, the center hand side is just partial phi square. We write.
This one? This one?
Yeah,
No,
the second.
this one.
No, sorry.
This one.
Yeah.
This one.
Yeah. So, and I think the delta I is a partial phi I phi.
No, sorry. I mean spherical coordinate in field space, not space-time space. Yeah. We still have Txij. Txyz. Okay, great. Now we have this. We can directly use everything here. Okay. I will just show this as an example. So I will show you the calculation. Now V, quartic. Then V1, V2, you can, this is derivative with respect to phi, okay, square. This is m plus square V phi V. Yeah, you can easily calculate, right? This is 8 phi square. This is 12 phi square. Good. Then if we require epsilon 1 to be 1 and also epsilon 2 to be 1, respectively, they give phi. Pay attention here, epsilon 1 is epsilon V1, but epsilon 2 is some combination of V1 and V2, okay? This is 2 this is a bit larger, right? This is a bit larger. So, which means that if we give you a potential like this, V phi, this is quartic, it rolls down during inflation. So which condition is satisfied first, then it determines the end value of phi. So obviously this larger, so it should reach this earlier. So we set this to be phi n. Okay. Right. And then E4 number, you just put this back. Phi divided by 4m Planck squared d phi. Then integrate phi initial minus 8 m plus square. Okay, this is nothing but this square. This is phi n, which means that this is just phi initial, square divided by 8 Planck square minus 1. Okay? Which means that phi initial, or maybe I should write here, which means that phi initial with Planck as unit is square root A E4 plus 1 square root. So if we take, just for some example, okay, 60 E4, this gives you phi initial divided by Planck is 2 square root 122. Then you can put it back to this. ns minus 1. ns minus 1 is like 0.05. R 0.26. Okay. Of course, usually we have to also calculate this. Okay. We need to match the CMB 10 to minus 9, but I just skip this. I just directly calculate ns minus 1 and R. Okay. Now let's see whether this is okay. ns minus 1 is 0.05, which means that ns is 1 point something. No, minus. Sorry, minus. Stupid mistake. Is 0.95. Okay, 0.95 is here. Okay. And R is 0.26. This is 0.15. So 0.2, 0.25, 0.26 is here. Okay. It's ruled out. Great. This doesn't work. Then people start thinking, oh, how to do this?
In the case of ruling out, yes, you can take into account the gravity part. Or...
No, we don't. We haven't taken internal gravity part. It's already ruled out. Yeah. Okay. Now this some smart guy introduced this nominal coupling. This can help to make this viable. And I think the oldest paper is 1995. Of course, at that time, we don't discover Higgs, of course. By this 7 Hayes, Kotta, and then. And then in 2008, this Petrokov and Shapchinikov they mention again, because at this time I think we already have discovered Higgs, and they mention, oh, this can do the job. And the same year, I think Stravinsky and his collaborator Babinski also Kamenschik, Stravinsky also write a paper about the standard model Higgs inflation, something. Yeah, but I think mostly people cite this one. But this is, I think, 3 earliest. So what we need to do is just to add one term about this non-minimal coupling. As I mentioned before, non-minimal coupling means the direct coupling between this scalar field and the Ricci scalar. This is the coupling constant, dimensionless. Okay, this is our starting point. And we again use the rewrite this, yeah, or not equal, but just we neglect the angular part. Yeah, but remember the angular part is useful when we discuss unitarity. Okay. Simple, just have some, how to say, effective mass term from CR. Yeah. I erased it. Sorry. Yeah, but yeah. Sorry.
It was the earliest.
Non-minimal. You mean conformal coupling?
It was non-minimal coupling and also
Yeah. But here I only means the Higgs. Oh, no. How to say? Oh, really? I mean this kind of coupling. I see. I only know his conformal transformation.
I think he mentioned this particular.
I see. Okay. Then I will add it here. H minus. Because in this paper, I think he mainly want to, how to say, try to find the Einstein frame of the R squared Stravinsky model. Yeah. So. Yeah. And one unnatural thing here is that, as you see later, this need to be much larger than unity. That's the point. To realize successful inflation. But I mean, nobody knows how we can get such a large coupling. Yeah, critical Higgs, we can be smaller, but you need extremely small lambda. So, yeah. Yeah, but anyway, all the discussion we just talk about this, and yeah. because when we discuss the UV extension, we need this condition.
What do you mean extension that still you be completely?
Yeah, I mean, I will show you that cutoff scale of this is low. It's like, so if this is much larger than 1, then the theory, the cutoff scale theory at a vacuum, it's suppressed by this, it's not up to n Planck. Yeah. And during preheating, you will involve some physics with scale higher than this. So you have strong coupling in this model.
We have here is the two scale, gravity scale and the field scale.
Mm-hmm.
And then in the viewpoint of completing is
I mean the scalar part.
both of them.
Scalar part. A gravity part is already like Planck. Yeah.
Okay.
No?
The quantum fluctuation original of the this is a game of the original nature of the fluctuation.
Mm-hmm. Mm-hmm.
And then with the quantum gravity, the just started near the Big Bang. And then we still there's some problem on completeness in gravity. Field scale is okay.
Mhm.
Viewpoint of the RG in sense. But
I'm sorry, no. Here, what I want is, this cutoff scale is for the scalar part, scalar sector, not the gravity sector. Yeah, the gravity sector is,
that point.
yeah.
A little worry about in the gravity side in for mysterious quantum fluctuations.
Ah, okay. Yeah, but, okay, unfortunately, I will not talk about much the graviton parts. Yeah, sorry. Yeah, okay. So we start to see whether this can be can realize inflation, successful inflation. So I will try to show just this one example, some Jordan frame analysis. Very simple. I will not calculate many things. Let's just show you. For C much larger than 1, actually, as you know, you have, in this R, you have second derivative on G, okay? So somehow this can give you, if you do integration by parts, give you some kinetic term to phi, which means that you get some kinetic term proportional to C. C is much larger than 1. So somehow we can neglect the original kinetic term for phi as an effective field theory, which give you something like this. Then we can solve the equation motion for phi. Equation motion for phi is what? Vary with respect to phi. So it's say z r phi equal lambda phi 3. If phi is not 0, then we have this. Then we can replace all the phi square with this. Okay? What you get is Starobinsky model, R plus R squared. So yeah, here I don't talk about Starobinsky model, but Starobinsky model is very well fitted to the observation. So as long as you require this combination to match the CMB which give you c over square root lambda to be 10 to the 4. Then this model is okay. It can be well fitted to observation. So this is the very simple analysis about this model, as long as this is satisfied. Of course, as mentioned by Song Chang, if lambda is extremely small, then we can avoid this very large C. Yeah. But here I only focus on this large C and moderate lambda, for example, 10 to minus 3 or something. Okay. Okay, so this is too complicated, Jordan frame. So we go to Einstein frame, where the gravity part is very simple. Okay. Yeah, I have one page of Jordan frame analysis, but it's too complicated. I define a conformal factor omega, capital omega square, to be 1 plus c phi square m plus square. Then you will see that this action, you can write it like m plus square over 2 omega square r, and the canonical kinetic term mv. Okay, omega. Now minimum coupling is here. Then we do the conformal transformation by Keiichi Maeda, Professor Keiichi Maeda. Then go to the Einstein frame. We go to the Einstein frame. Einstein frame. We change all the metric, okay? This also, R is determined by the GE, not G, minus GE mu nu, chi, say V, okay, V tilde chi. So what is chi? Chi is some, why I don't have the complete expression. Sorry. Yeah. Chi is defined by this canonicalization of the kinetic term, 1 plus 6 c square phi square divided by Planck square and omega square and omega square. Something a bit complicated. And V no, it's omega 4. Square, okay, square. Okay, yeah. V chi is this, but it's phi in terms of chi. So we need to change all the phi to chi and omega force. And you can write it, I just omit this, okay. So the conformal factor comes to the potential like this, and we canonicalize the chi field like this. Then we go back to what we are familiar with. But the problem is it's difficult to integrate this one. No problem, because during inflation, you can simplify things during inflation. Phi is much larger than this value, Planck over square root c. So some terms inside can be neglected, which after the approximation, you can integrate to get the relation between phi and chi, approximately exponential chi divided by square root 6 m Planck, something like this. Then you can rewrite the potential. V tilde chi is okay, now we have potential, we have everything. And this looks like, and we don't know this part because we only know up to this Planck over square root c, okay? Oh, no, then maybe no. Then maybe some value. Very flat for large value of phi. Okay, great. You can repeat. You can repeat. All replaced by chi, okay? Chi. You repeat. Something like this, and e to minus I. And also we need, this time we need to calculate this. This is roughly pi square lambda c square and some e to the 2. Yeah, maybe you can do it. Yeah, I just. Oh, okay. Yes. I mean, you can do it. You can do it. Okay. Yeah. times e to square root 2 over 3, 1 plus e minus square root 2 over 3 squared. Okay. Yeah, ns is ns minus 1 is. Okay, so I will only show these two examples. Okay. Yeah. Great. And then you require them to be to be satisfied. Then you have 1 over 2 square root 3 over 2 log 4 to 3 and plug. Square root 3 to log 4 over 3 plug. Which means that this chi end is determined by this, not this. Which means that, okay, this thing, this is roughly 1 over 6 square root and plug. This also can translate to phi, the original one. Phi is, roughly speaking, this value. So our calculation, the statement here, okay, is good. Because when phi is larger than this, then the inflation can happen. And also n you can calculate. Replaced by chi. I will omit this. Then you can do it by yourself. It's nothing but the, okay. So if you take NE to be 60, then chi initial is around 5.4 plug, something like that. Okay. Of course, you can write it in terms of n, not like this. Then, requiring this to be 10 to minus 9, you will, and put this back to here, and requiring this to be 10 to minus 9, then you will recover what I said before. Yeah. The same. And NS looks like minus 2 NE minus 1. Okay. So writing this in terms of NE is homework. So you can express in terms of this. And if NE is much larger than 1, then we can omit 1. It's like for 60 evo, right? 60 evo. This is 12 NE squared. 0.003. Okay. This form is exactly the same as the Stravinsky model as I analyzed in the Jordan frame. So in terms of inflation predictions, NS are something, it is the same as the Stravinsky model. And you can see here, right? NS is 0.967 here. R is 0.003. This is 005. So 003 is maybe, oh no, this is 005. 003 maybe here. Okay. Good. For smaller n, for example, 50 E4, then ns minus 1 will be larger, so ns will be smaller. So you move to this way. Inflation scale. If you still remember, is it? Ah, here. Hubble scale during inflation. So yeah, this is important when we discuss unitarity. Right. So this is good. I will erase this. Five to six. Probably it's root. You mean 5 to 4 plus 5 to 6? I haven't tried, but probably for large field value, the 5 to 6 will dominate. Yeah, and probably will change the prediction. Yeah. Sorry? I'm not sure. Yeah.
The phone is right at the sweet spot using the flat plateau. But if you have 5 to 6, it is points. So 5 to 6 should be small. How about cubic? Cubic is okay. 5 to 4 is
No, I mean, basically it's a Higgs, so
you
you can think of, you know, you can keep.
So I think that some kind of phase transition, including
Yeah.
the assets. Sorry about that. You have to take into account Higgs.
Yeah, yeah. Six. Yeah, probably I can take it down. Sorry? Sorry. Okay. So we know the inflation predictions about this Higgs. We call it metric Higgs inflation because we only consider GR. Okay. Before going further, we want to look at, here we only focus on large phi. So let's have a look at the small phi. Okay. Because we still don't know the potential here. In the regime where phi is like this, you can also do some approximation, and you find that chi is proportional to chi is proportional to phi squared, which means that the V is quadratic for this canonicalized field, quadratic potential. For even, okay, maybe I should make this. For even smaller phi, chi is almost coincide with phi. So you have quadratic potential, which means that you have quadratic and sorry, quadratic. This is important for reheating. So now I discuss the unitarity property. Unitarity violation. Unitarity violation in metric Higgs inflation. Metric Higgs. So to discuss this, first we need to know the unitarity violation scale in this model. Okay. In the scalar sector. And I think the first paper, this unitarity violation scale have been discussed by many people. They calculate different ways and something. And for me, the first one to point out that this unitarity violation scale has something to do with the multi-component, multi-Higgs component. It's by the Hertzberg's 2010 paper. Because for single field, you can always canonicalize, and then all the contribution is from the potential, so you just look at the potential. But for multi-field, this kind of canonicalization that doesn't work usually. So it means that you always have some complicated kinetic term. Okay, and he points out that this complicated kinetic term is responsible in this Higgs inflation case for the cutoff scale. Okay. And in general, of course, in the okay, I have erased it, but okay. But this is the first paper about this multi-field effect. In the Jordan frame, JF, Jordan frame, it seems okay because if you remember, all the things, complication is from omega. and you have just delta function. I mean, not delta function, but flat field space. If you regard this as some kind of coordinate, you have delta ij field space. And you have normalized, renormalizable potential, with small lambda, then it's okay. Then everything should come from this. And this is flat. And in Einstein frame, somehow, it's very complicated, the kinetic term, and you cannot canonicalize it when you view this as multi-field. And yeah, what do you say? This should be G Einstein frame Ij. And some complicated potential. Something like this. This is non-trivial. This is not flat. Okay. This is Gij. Yeah, fortunately, the potential is still quite simple. Yeah, complicated. And you cannot canonicalize all of them. At most, you can canonicalize one of them. So this is curved. And then this argument becomes a bit strange. Why in Jordan frame you have flat and Einstein frame you have curved? And when you calculate, for example, the curvature, if you say the curvature of the field space is related to the cutoff scale, then which one we should trust? Something like that. Then maybe I should. Actually, we can have some frame-independent way to calculate this thing. No matter which frame you are in, you get the same result automatically. But I will introduce this tomorrow. So sorry, I don't have enough time. But the basic idea is that if you expand, you expand this. Okay. If you regard this as a metric, you expand this. Maybe I should use it. Then, for example, around zero. Okay. Then you have probably delta ij. Right, yeah, delta ij. Plus something also phi ijk, probably ijk, plus some second derivative phi del phi d phi. Okay, this is good because first derivative on the metric, as we know in the GR, is related to the connection. Second derivative is something to do with curvature. Okay, so if we consider, and somehow we can always find some coordinate. Of course, the result is coordinate independent, but to see the simple argument, we can choose some coordinates always. The normal coordinate we will say. we can vanish this. So we only have this and this. Okay. But this choice is not necessary. Okay, then if you consider some scattering amplitude, L phi I, phi j, phi k, phi l. Then the scattering amplitude is simple. Not simple, but it can be expressed in terms of phi I, phi j to phi k, phi l. In terms of KLJ plus some JLK. This bracket is symmetrized in the indices IL, JKL. Okay, given by the symmetry, the curvature of the field space. And S is the Mandelstam variable for the corresponding species. Okay, great. This is given by some paper and Nakai, Tanabashi, Tsumura. 2019, and also some paper by Cohen, Craig. These people study the effective Higgs effective field theory or something. Sutherland. Yeah. Which means that such kind of scattering amplitude, given G, you immediately know, as long as you can calculate R. So now the problem is how to calculate this R in a frame-independent way. And I will talk about it tomorrow. But anyway. Given this, then, just require this to be smaller than 1, and you get some bound. So this, and roughly speaking, if we all of these are taken this bar is taken at the vacuum. This can be finite, but I just use this example, but this can be finite. So these are all taken at phi equal V. V is finite, okay? So roughly speaking, the cutoff scale of the metric Higgs inflation, the ratio between this and the graviton strong coupling scale, I would say n Planck over square root of n, something like that. Yeah, but the ratio is more important. The absolute value is nothing, but just the ratio is given by, roughly speaking, the curvature square root divided by this gravity cutoff scale. Okay. So we can calculate, tomorrow I will introduce a method to calculate this in a frame-independent way. So now obviously this is 0, right? R is 0 because it's flat. This is not 0. So you cannot do that. But yeah, we can manage to do it in a frame-independent way. Then you can do it in any frame you like, which is simpler. Which simple, you can do it in whichever frame is simple.
So this formulation
Yeah.
here,
Yeah.
does it apply to Any frame or only in Einstein frame?
I think it's I think in this expression they don't consider gravity. They don't consider gravity.
Without gravity.
Yeah, in these papers, no gravities.
So both paper.
Yeah, they are considering standard model EFT, Higgs EFT. Yeah.
So can I understand this scattering as a self-interaction when looked in the Einstein frame?
Yeah, kind of self-interaction in the kinetic term and in the kinetic term. Yeah. Because here as you see 4 point, right? Yeah, so it's related to R. Yeah. Yes. Yeah.
This the curvature in the field space.
Field space. Yes. Gij, not small ge mu.
Oh, I'm sorry. The
Yeah.
Einstein frame is not say.
Maybe I shouldn't. Yeah, I just use that as example.
There is the Einstein frame. It starts with Einstein frame.
Yeah. Then you can expand. Yeah, but of course you can do it like Gij, but Gij is just delta ij.
I understand that point, but in the case of the Einstein frame.
Yeah.
You can expand on.
Yeah, some frame. Yeah, you can expand.
Okay, that's I think that you mean set up the Einstein frame for Gij, and then you can expand it.
Expand, yeah. Around some vacuum. Here I just take to be 0, so yeah. Around some vacuum, you can do it.
And then we'll see. Already explained the second term is the regulative.
Yeah. You can always choose some normal coordinate.
Yeah, which frame? The independent frame.
No. Any frame. Yeah, just general. Given any general Gij or G mu nu, you can choose some normal coordinate where this is 0 locally.
Locally.
Yeah. But this is not 0.
In the case of the one you have the take into account the single field case.
No, this is multi-field because you have Ij.
Sorry.
Yeah.
And then still you have the I think you have the you want the frame independent for this kind of thing.
Yeah, I will introduce tomorrow. Yeah. Now I don't have much time.
Okay.
Sorry. Yeah, so this, I think it's quite interesting.
Yeah.
And pay attention. Please notice that if for single field case, you can always canonicalize the field, so you don't have to do this thing. One dimensional, it's always trivial. So then with this method, you can recover all the cutoff scale in the literature. Okay. For example, for n is ijkl equal 1 to the n. Of course, in the standard model Higgs is 4. Okay. So now I just, for general n, for n equal to this ratio is this is the finite vacuum expectation value for the phi, and for different value of the v. Yeah, that's why I said when we talk about unitarity, we need to take into account all the components because it's multi-field. And for n larger than 2, which is our standard model case, this is one. Same range, field range. Okay. So the cutoff scale actually is changing with when phi is moving. At the vacuum, for example, V equals 0, at the vacuum, at the here, standard model case, you have kind of en-Planck OXD. But during inflation, for large V, during inflation, it's a little bit larger. En-Planck over square root C. Okay. So this is a bit higher. And now we can compare with this. And you see, compare with the cutoff scale during inflation, the inflation scale is a bit smaller due to the lambda. So during inflation, there's no unitarity violation, it's still below the cutoff. But during reheating, around the 0, the V around 0, the cutoff scale is a bit lower than the inflation. And then we need to find out during preheating or reheating whether we have something that is larger than this cutoff scale. Okay, this is during inflation. This is around V equals 0. Okay. How many pages I left? Yeah, probably. Yeah, I need to continue tomorrow. Yeah. Probably I need to end here. Sorry. I still have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14 pages. Yeah, but I can do it tomorrow. I can do it tomorrow. Yeah. So, sorry for the long time.
Yeah, thank you very much for the nice lecture of the first day. And today we will have a seminar dinner soon after this one. So I have reserved the Italian restaurant name, with name Nova Italiano. Nova Italiano. Yeah, in front of the Kyunghee University. Yeah, so maybe since it's already 6 p.m., we can just move out, maybe gather at 6 p.m. In front of this seminar room and then go together. Yeah. Maybe in front of this seminar room. Sorry? First floor? Okay, yeah. Let's meet the first floor is around 6 p.m. Yeah.
6:10. Okay. 6:10.